www.nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Okay, we'll get started now. This is lecture 16 on carrier transport. By carrier, I mean electron and hole transport. Finally, they will be moving in response to an electric field or a density gradient. I'll start with an overview. I want to bring you back to the bigger picture of where things are. And we'll talk about drift current as one component of current. Drift current is something when you apply an electric field, electrons and holes respond to the electric field, and so they begin moving, and that's drift current. And in relation to drift current, we'll discuss the physics of mobility. Mobility is scattering-dominated transport, when the electric field says, go as fast as possible, but everything around it says, like friction, that slow down. And that physics of slowing down is encapsulated in mobility. And we'll see that mobility is generally associated with low field transport, meaning when you apply a small electric field. But these days, you know, the MOSFET or the transistors we talk about, they have, for 20 nanometer channel, they apply a volt. And many times on a gate oxide, which is maybe 1 nanometer thick, there's 1 volt on it. I mean, tremendous amount of field. It is like 1,000 times more than the power line, the high voltage power line that carries electricity to our homes. It is 1,000 to 10,000 times more of that field. That anything survives is a remarkable thing. And we'll see that. But I want to show you at high fields, there's many more interesting things happening, and some physics of that we'll discuss and then conclude. So where are we? We started this semester by discussing that if you put a semiconductor or a metal in between two contacts and apply a voltage, then the current flow depends on the material itself. Silicon, germanium, gallium arsenide. Count the atoms, and then you'll try to see how many electrons you have. And in fact, that is what you have tried to do. By using quantum mechanics, it told us where the electrons can sit, density of state, remember, effective density of state, and equilibrium statistical mechanics. That is, I'm not applying any external electric field, no light shining on the material. In that case, we were able to calculate the electron number n by first finding the Fermi level in response to various donors and acceptors. And from that Fermi level, by using the charge neutrality condition, remember, n and p, that all this must sum up to 0, that we used to calculate the electron density. So we were happy with that, because that allowed us to calculate electron density at multiple temperatures, right? Do you remember? But in that discussion, there was no mention of electric field. So that's why you see I keep using the word equilibrium statistical mechanics. And now we are talking about velocity, the other ingredient of calculating current. And the velocity, calculation of velocity assumes non-equilibrium statistical mechanics. You shine light, excess electron hole pair, as a function of time, these are disappearing through various channels. So that is not any longer in equilibrium. So that is something we discussed in the last class. Today we will expand on this a little bit more. So chapter 5 was when we had a semiconductor sitting there, shine light, and it is like one contact, because light is coming in, exciting electron hole pairs, and then letting it go, light is coming out, or the heat is coming out as a result. Today we'll talk about flow of electrons when they are in between two contacts, and the two contacts have created an electric field in the semiconductor. One thing I should mention, although I didn't draw it, it's very important that anytime one draws a picture, that one of the terminal is grounded. Because without a ground or without a reference point, later on you'll see it's sort of difficult to keep track of all the electric field and the potential and charges. So ground any one, doesn't really matter which one it is, and we'll set that one to 0. If you ground, for example, to the right-hand side, set it to 0, then the left-hand contact will be at negative potential. If you ground the left-hand contact, then the left hand is 0, but the right hand is at a positive potential. Potential difference is what it matters. Absolute value of potential doesn't mean anything. So you can ground any one of them, but ground one to make sure that we are talking about the right reference. Okay, so what are you going to do at this end of maybe 3 more lectures? What we're going to do is to derive a set of equations. And if you know this set of equations, you know, every semiconductor device that is made, either for your laptop or for the interplanetary mission, when they send things out in space, physics essentially, there are sophistications, but essentially will be described by the equations I talked about. Just little 5 equations, that's it, nothing more. And everything will come out of it. And the rest of the course is actually the application of this equation, solution of this equation to various cases. Analogy is like Schrodinger equation. Once you know Schrodinger equation, you solve it for a wide variety of cases. Similarly, this transport equation, once you know it, then you apply it and solve it for various approximation in various cases. So, the first equation is called a Poisson equation, which relates the electric field E or the displacement D with the charges. Now, when you have homogeneous, then of course the right-hand side of that equation is 0. So no variation in the electric field, homogeneous. Okay. Now, when things are not homogeneous, of course, that's when things become interesting. Then the electric field as well as displacement D, that keeps changing from point to point. So we'll have to solve for that. Poisson equation is number 1. Second is the continuity equation for electrons, for example. There are lots of electrons in the conduction band moving around, and I will explain each one of the term. Now, the term that is J sub n is the electron current. And you can see G sub n is a generation rate, shine light, last chapter, then that will be all the physics that we talked about is hiding in G sub n. R sub n is a recombination, OJ recombination, direct band gap recombination. You know, all those recombinations we talked about in last 2 classes, those are hiding in there. And we'll derive that in the next class perhaps. Now, these 2 are for electrons and these 2 are for holes. Same equations. You will notice a little bit change in the sign. In one case, you see you have minus 1 over q. In another case, the second equation, you have plus 1 over q. Why? Well, electron has minus q charge, other one has plus q charge. And you can also see that the gradient of n and gradient of p in the third and the fifth equation, they also differ in sign. Why? Because this is diffusion, we'll show. And diffusion doesn't care about whether you are charged or not charged, right? Because you put anything, whether a drop of ink in water, uncharged, or electron in one point, or hole in another point, they diffuse essentially using the same physics. So therefore, they have different signs so that once you put it in the second and the fourth equation, they have the same sign. We'll come back to that. We'll see how it works. So today, my goal is to explain the physics of that term. Poisson equation, presumably we have talked about it before. Remember, from potential, we drew the electric field, and from electric field, we did the charges. Do you remember this? So that was my discussion about Poisson equation. We'll not do that anymore. We'll apply it and you'll see how it works. But today, I'll talk about the drift of electrons in response to an electric field E, and mu sub n is the mobility that we'll talk about also. So let's talk about drift current. Now, before I move on to discussing drift current, let me remind you that what approximations we are making, because this is for the first time we are really going away from equilibrium to non-equilibrium case, applying an electric field, currents are moving. So we'll have to think back a little bit about the approximations we made and why we can continue to make those approximations, because it's not really obvious anymore. You remember this question about free electron mass and effective mass. When a free electron with a red circle there moving with a free electron mass of m0 in a periodic set of potential, I compared that situation a few days ago in terms of as if there is a runner, sprinter going over a set of hurdles. And instead of keeping track of the hurdles and solving the whole problem correctly, the blue potential where the electron Coulomb potential is attracting repeatedly the electron as it is passing through is shown, is given in U crystal, U subcrystal, that's the one. And U external, what is that? That came from the battery. So we now have a battery, so we have to put that extra piece of potential in the Schrodinger equation. If we solve this equation properly, then actually we should have started going back to ground zero, started the Schrodinger equation all over again. But that will be too much torture. So we'll not do that, but rather what we'll say, and then I'll explain the approximation in a second, that we'll forget about the blue potential going up and down, bobbing up and down, and hide everything, all the physics of it, the interference of it, all in the effective mass. So therefore, we'll not talk about the U crystal anymore. And therefore, you will replace, you see previously in the first Schrodinger equation, I had m0, the free electron mass. In the second Schrodinger equation, this is called an effective mass equation, I have m0 star, because that hides the crystal potential within it, right? Okay, now the U external is of course there. Now, one thing I want to immediately point out that we are sort of heading into a little bit of trouble here. Because remember, when can we define an effective mass? It required the solution of the Schrodinger equation. Solution of the Schrodinger equation required that the potential of each little piece is periodic, right? That is how we folded back the equation, periodic boundary condition. Do you remember? That is how we got the effective mass. Now, as soon as you put an electric field on it, then of course, the periodicity of the potential is gone, right? And so, this extra space, extra transformation of effective mass in the presence of an external potential is not really 100% correct. But what we'll ask you to do when you go home, calculate the magnitude of these two quantities. Calculate when you have an electron, 1 nanometer, that's how far away the electrons move around, 1 nanometer away from a proton. The field will be on the order of 10 to the power 8 volts per centimeter, on that order. You know, Coulomb electric field, so calculate that. Compare that with the maximum electric field your Pentium is handling, which is maybe on the order of 10 to the power 6, 5 times 10 to the power 6 volts per centimeter. So, any potential that you can conceivably put on your device is actually far smaller than the potential the electron sees within the device. And as a result, even if we make approximation, this little potential U external is not going to change the periodicity in a fundamental way. You'll have to go about 100 or 200 atoms before you see a significant change in the potential. That's why we are still able to keep this view, even though the whole system is no longer in equilibrium. Okay, so let me now very quickly discuss this issue. Let's say I have drawn the conduction band diagram. I haven't drawn the valence band diagram here. And I see that the potential or the EC, the conduction band energy, is changing with position. That means I have an electric field here. And you always remember, right, that at each point, really, there's the EK diagram sitting there. When we draw a continuous line, actually we are folding back all those information in the effective density of state. But in your mind, anytime you see a line, there should be this thing sort of in the back of your mind. We'll not draw it all the time. And then there are, of course, some electrons going in the positive direction. You can see on the positive branch of the line, and some going in the slightly negative direction. And those electrons, as it moves along, they will scatter and they will go down the hill. It is like somebody, a skier, is going down a downhill slope. Now, instead of looking at this complicated picture, we will transform it something simple. We'll say, well, we don't have that many electrons. Everybody going in their different way. We'll assume sort of an effective representative electron, which moves with an average velocity, so that it sort of reflects the chaotic motion of all the electrons on the top. Because we know that after you apply an electric field, everybody as a whole, as a crowd, is going to move downhill. But instead of thinking about the swarm of electrons moving downhill, we'll take a representative one and then think about how it is moving downhill, and from that back calculate what the group is doing. So here I show instead one electron moving through the effective density of state downhill, representing the previous case. Now put a bunch of crosses there. The cross simply means that the electrons cannot go on its own without scattering. Scattering with what? I will tell a little bit later. It is like friction. When you put a pedal on your put extra gas in the car, then initially it accelerates. But very soon the friction and your acceleration, they balances, and you move with a constant velocity. So that is this extra crosses is representing that friction, the nature of friction I'll discuss in a minute. How the electron, in response to an electric field. What is the electric field, by the way? Because this potential is changing from a top value to a smaller value, gradient of that potential is the electric field. You can see the gradient is constant, and so I'm assuming that there is a constant electric field pumping the electrons along. Now the equation I have written is an equation for this is Newton's law, right? I've said that change in the momentum as a function of time is equal to the force minus QE. Why minus? Electron, right? Minus QA. And if you have friction, then the momentum will relax. If you didn't put any electric field in it, eventually it's going to stop completely. The third term on the second equation, or the second term after the equal sign, that's the momentum loss because of the friction. And the physics of tau sub n we'll talk about in a little bit. But do you see why we have put Mn star? Because we have hidden all the crystal information in that Mn star. And so the only extra electric field we are thinking about is QE, that E is coming from the battery. Do you see that? And the crystal potential are all gone. So we have that now. This is not an equation that we are afraid of. We can solve this, and if you solve this equation, you can very quickly see, if you plug it in the other one, that you will get an equation like this. How does this equation look like? You can immediately see that when time is long, how long we'll say in a second, when time is long, then the second exponential term, that will drop out, right? That will drop out. And then we'll have a term which is proportional to the electric field, which makes sense, right? After a long time, friction has equal to the force, and we are moving at a constant velocity. Now, what about at a very early phase in the time? You know that exponential will be expanded in 1 minus t divided by tau, right? E to the power x when x is small is essentially 1 plus x. And in that case, you will see that in very early phase, when you're just accelerating 0 to 60 in 6 seconds, don't they say? When they accelerate a car, that is what they're talking about, that when you pump the gas, then initially it will go linearly, then the friction will catch up with it, and then it will go with a constant velocity. So that is the essence of this. It's a high school physics of a ball rolling down a incline with friction on it. And so that is what I have written here or shown here on the bottom right picture, in which I plot velocity versus time. Note very carefully that the x-axis now is time. I'm going to show you another figure a little bit later where the x-axis will be electric field. But now it is time. I'm thinking about starting a car, pumping the gas, that's the initial linear part, then friction catching up, and the velocity saturating. Now, the saturation velocity is something I'm going to think about. Again, now what is that time tau? I will explain what that time is, but right now, or where the time constant comes from, but that time is on the order of 1 to 2 picoseconds. Because within a picosecond, everybody catches up that this guy is moving very fast, we have to take some energy from it. So scattering begins within a few picoseconds. And this is a number I have told you before. Do you remember when? Do you remember I said when the electron and hole see each other, every time they see each other and bump into each other, they don't recombine. They scatter on the order of a picosecond, the same number. They scatter against each other on the picosecond, but only when their wavelengths are just right, only then they can recombine. And that is 10 to the power minus 9 seconds or a millisecond for indirect band gap, indirect recombination. So that is the same time here. They see each other very frequently. And therefore, this time is, so within a picosecond, you essentially can approximate the velocity within something being proportional to the electric field, and you don't have to worry about the early part at all. You see, now picosecond, how fast a computer can you make with a picosecond? It will be on the order of 1,000 gigahertz, let's say. And you don't have a computer for 1,000 gigahertz. So every computer you make, you can assume that the early part as if doesn't exist, right? We have in these days maybe 100, 200 gigahertz, that's individual transistors, and Pentiums maybe 10, 20 gigahertz, something like that at most. So as a result, we will always worry about just a steady state. But I'll give you an example where you have to think about the very early phase. So instead of carrying around this q tau n divided by m star term around, we'll call that constant a mobility. So for the mobility, q we know, charge. Effective mass, well, we spend many classes on that. The only thing we don't know of physics of tau sub n. And if I somehow know the physics of tau sub n, then I am set. I can calculate mobility. I can say when you put a battery, how fast the electron goes. Okay, so next few slides, hopefully, we'll talk about the physics of mobility, or equivalently, the physics of scattering, how fast they scatter against each other. Now, one thing you can easily see that before we move on, that if your electric field is E1, then the velocity at which you will saturate, that will be a little higher. If you put a little bit less gas, and then it will move it a little bit, saturate it a little bit slower velocity, right? That we know. And so, if we are just interested in the final velocity, for our typical transistors, then we realize that the velocity is almost linearly proportional to the electric field. So the saturation velocity, you will see if we just interested on those points, we can pick up the red line, the saturated part, the blue line, and plot it also as a function of E1 and E2, and that will also give me a characteristics that I'll be interested in. But here they're saying the current is proportional to the electric field. Now, if I keep putting higher and higher electric field, do you think I can get infinite amount of current? Well, that's not happening, and we'll explain why. Okay, physics of mobility, let's talk about that. So physics of mobility means physics of the scattering, the why something scatters and how fast it scatters. Okay. Again, that same picture of electronic potential moving up and down, and an electron trying to move it. This was the original picture, and we replaced it with the effective mass. Now, the first type of scattering that we'll be talking about is ionized impurity scattering, or impurity scattering, and I will explain the physics, but let's first look at it from this point of view. Assume that I had a series of identical atoms, I take out one atom, put back a new atom in. When I put back a new atom in, its potential is not the same as before, right? Obviously not. So in that case, let's say I move back that electron in. Now, if I wanted to keep my description of effective mass, then what do I need to do? Then I need to say, okay, I have the red potential, but I will approximate it with my original blue one and put that potential in the effective mass, and anything remaining, the difference between the red and the blue, I will put it as an extra potential. You see? At this extra potential, when this electron with this effective mass is moving, as if it will scatter against this extra potential. And when it does so, then it will cause the friction, and this will slow down the electron. Okay. Now, how does it look physically? One way to think about it is think about a piece of semiconductor, right? Donors sitting at random points, decorating it as random points. The donors have given away its electron. Now it is positively charged, right? So it's like a pudding with raisins sitting on top, all positively charged. Now an electron is coming in. As soon as it comes in close to a donor, it says that don't go directly. It will try to bend it towards itself, right? And the electron motion will continuously be bent by these positive charges. And this is, so it's perturbing its momentum, and this is a scattering. And this is called a ionized impurity scattering, because only when it's ionized, then it's going to scatter. Same for the acceptors. Negative charge, when electron comes in, it says the negative charge sitting in the space, and it scatters. Okay, and we will discuss a little bit more on that. Now, this is something you are not supposed to learn in this course. You'll learn in detail in another course, in 656, for example. But the point is, this extra piece of potential with a little bump in the speedway, that potential, if I call it U, it is possible to easily calculate how frequently electrons scatter by a specialized formula, and that formula is called Fermi-Golden rule. Now, all I'm saying that there is a way to calculate it. I'm not telling you exactly how to calculate it. It will not be in the exam, so don't worry about it. But the point is, this is how people would calculate this type of scattering. So there is two types of scattering that are of great interest, that slows down the electron, right? One is called a phonon scattering, and the second is one called ionized impurity scattering. Now, ionized impurity I just explained, right? When you have these charges and they try to deflect the electrons, slow them down in the process, ionized impurity scattering. And the ionized impurity scattering is inversely proportional to the number of ionized donors. Does it make sense? If you have more, right, it will scatter more frequently, and therefore the time will be shorter, right, for the scattering. So it's inversely proportional to n sub d. If you have n sub a acceptors, then it should be inversely proportional to n sub a. Now, why is it just n sub d? Why is it not n sub d squared or something else? The reason is, remember, the donors' atoms are very few, relatively speaking. 10 to the power 22 number of atoms, silicon atoms, right? How many donors? 10 to the power 18 maybe. So they are far apart. And so once the electron scatters with one, then it forgets about that electron, that scattering altogether. It goes a long way before scattering one more time. Therefore, it's linearly proportional. If they were very close together, heavy doping effect, then I couldn't simply say it's 1 over nd. You see? Okay. Now, why t to the power 3 halves? Well, that has to do with screening of the electrons, because anytime a positive atom sits, it doesn't sit alone. It sort of brings around it a bunch of other electrons to screen it. And so when a new electron comes in, it not only scatters with the positive one, but a sort of surrounding, it's like a king and the court, sort of the court. And if you want to see the king or get scattered by the king, then you have to sort of get through that electron cloud or the people around them. And so that is where this t to the power 3 halves comes in. But that you will understand a little bit later. Has to do with straining with other electrons around the positive core that does this, modifies the scattering. Okay, so that's one part, and this is the extra piece I just told you about. Now there is something else, phonon scattering. What is a phonon? Phonon is this lattice vibration of the vibration of the lattice. And what happens when an electron comes in, the lattice is vibrating. Sometimes it can steal a little bit of energy from the vibrating lattice and go up in energy a little bit. Or if the electron has a lot of energy, then the lattice, once it scatters with the lattice starts vibrating on its own. And even it doesn't give back the electron its original energy, but rather it dissipates it in the environment, right? So it's stealing energy from the electrons, setting itself into motion, and letting the motion dissipate in air. As a result, as far as the electron is concerned, this is a friction which is taking away its energy. Now, why is it inversely proportional to T? Because at higher temperature, there is no more phonons, so it can scatter more often, and that's why it's inversely proportional to T. What about these 3 halves? Because after scattering, the electrons essentially has to stay almost at the constant energy surface, and that's proportional to kT, the density of state. So this point isn't very clear. I will probably insert another slide later on, but for the time being, let's say the phonon scales with T, and therefore the scattering time goes down as inversely proportional to T. And the phonon essentially is a vibration of the lattice atoms, and that you will. So as far as the effective mass electron is concerned, it will see as if a potential moving up and down. Once you subtract the blue, the equilibrium position out, then you will see as if the extra piece of potential is bobbing up and down, and that's what this scattering is all about. So when you have, instead of one scattering, if you have a bunch of them, then what people do is they say that the scattering sum up linearly as 1 over. Does it make sense? If something scatters every once in 10 seconds and something else scatters every other second, together, do they scatter faster or slower than 10 seconds? It will be less than 2 seconds, right? Because most of the time it will scatter with 2 seconds. Once in a while, the 10-second one will come in. And so it has to be inverse of the scattering time. Do you see? Not just summing it up. Summing it up will give us the wrong physics. Now, beyond this, there's no justification of this rule. This is an old rule before almost quantum mechanics. And so this is really an empirical rule, no physics here. And because the electron can scatter with phonons, with ionized impurity, with all sorts of things, we sum them all up, and the mobility, the net friction, will be a combination of everybody, because everybody is trying to slow it down. Now, if you see that 1 over mobility is also proportional to 1 over the scattering time, so if the scattering times comes as the inverse, the mobility of various pieces will also come at inverse, right? If there are just phonons, 1 over mu phonon. Just ionized impurity, 1 over ionized impurity. But of course, everybody is trying to slow it down, so the net electron mobility is the inverse of all this. Let's flip it. If I flip it, then that's my mobility. Now this one, I could have ended it here, but most people write it this form. The subtract of a mu minus, a mu minimum, plus add it and subtract it. Now this could be an arbitrary value. And they write this piece, the second piece, as something that is proportional to the number of ionized impurity, n sub I. Do you see in the bottom? That, and then in n naught. Now these constants depend on energy. Where is the phonon scattering hiding? It is hiding in mu naught. So it will hide in mu naught, and it will also hide in N naught. And where is the ionized impurity? Number of ionized impurity, remember N sub D? That is that N sub I, because I could be acceptor or donor. So therefore, I have just written N sub I. Alpha is a constant between 1 and 2. Okay, so this is it. And this is called a Matheson's rule. And this is experimental values. In the x-axis, we have NA or ND, which in that expression is equivalent to N sub I, right? So you start with mu minimum on the right-hand side. Why do I start here? Because when N sub I is large, infinity, right, very large, then the second term will drop out. Only first term will remain, right? So therefore, on ND equals infinity, 10 to the power 19, then we start with mu minimum. Now, as you go make Ni smaller and smaller, in the limit of Ni equals 0, then your final answer will be mu minimum plus mu naught, right? That will be a little bit more. So you can see the curve going up, and in between there is a transition. So the initial early part is completely phonon dominated, no ionized impurity. The later part is a combination of phonon and ionized impurity scattering. Now let's look at some numbers. So what would you say the maximum velocity electron can go, or mobility an electron can have in silicon? On the order of 1,000, right? In silicon. For the holes, it is a little bit less, by a factor of 2. That's why when you design transistors, many times your NMOS, we'll talk about what NMOS and PMOS is later on, but one type of transistor that depends on electron is actually half the thickness, half the width of the other one, because holes move slowly. Holes effective mass is more, right? That's why it moves slowly. So that's the result. We'll have to take care of it in the circuit to that they all provide the same current. Okay, so that's it. For the time being, we'll just stay it here, but the physics, I cannot even begin to touch it. That is so beautiful. Hopefully in other courses you'll learn about it. Similarly, a temperature dependence is very important. Again, why this T to the power minus 3 halves is coming from? At high temperature, lots of phonons scattering dominates, and that's what I said a few seconds ago, right? Few minutes ago, that the phonon scattering goes as T to the power minus 3 halves, right? Do you remember? And that's why this mobility is also proportional to, goes as T to the power minus 3 halves. So high temperature, electron doesn't move as fast. It's scattering too often with phonon. That makes sense, right? That's no problem. And you can see in the inset that the exact experimental value is not minus 3 over 2. Minus 3 over 2 comes from theory. But if you look at the inset in the figure and in a log-log plot, it shows T to the power minus 2.3. So experimentally, it's a little bit more. Lots of people work on this, that why it's different, but that's a separate story. Now we'll start in the next 10 minutes, talk about high field effects. Whatever I said now is sort of true if you put a kilovolts per centimeter on that order, maybe 1 kilovolt per centimeter. And maybe in Apollo days, or maybe, when the Apollo went to moon, maybe in those days we had that type of field. For last 30 years, those type of fields are not in the present our devices. So whatever I said is good, but not good enough for electrical engineers. What happens when you increase the electric field too much? Then what happens? At some point, no matter how much you put on the gas, you cannot increase the velocity anymore. So we'll see why not. What I have plotted this time is velocity as a function of electric field. And as I said, in the early part, it is directly proportional to the electric field. Now, unfortunately, I have a typo there. It should have been mu. Mu is proportional, mu is a constant, but the velocity is linearly proportional to the electric field. Oh, I had it there. Okay, that's fine. But if you exceed a critical electric field, and for every material, the critical electric field is slightly different. if you exceed a critical electric field, no matter how much you pump in the electric field, electrons are not going anymore. And that number, called saturation velocity, is on the order of 10 to the power 7 centimeter per second, almost for all materials. That's why changing silicon to gallium arsenide in modern technology may not always help very much. The thing is that this velocity, saturation velocity, is a number which is almost independent of material. We'll explain where it is coming from. That's the critical electric field. So anytime you do a calculation, you should always check whether you are above the critical electric field or below it. Once you are above the critical electric field, then the expression I show on the equation on the top right, V is proportional to electric field, of course, but look at this expression. In the denominator, it has E minus EC. So when E is equal to EC, then that's 1, right? So then it will be mu naught divided by 2. But if it is much higher than EC, then do you see that the electric field will cancel? Do you see that? Electric field will cancel. And what would be my velocity? Mu naught multiplied by EC, the critical electric field, constant independent of electric field. So that is how it will saturate. Now, what is the physics of all this, right? I mean, why does it do so? Let's focus on the silicon conduction, silicon electrons, which is starting from 10 to the power 5 or so centimeter per second and at a low electric field. And then you can see that curve is saturating on the order of 10 to the power 7 centimeter per second. Why does it do so? So this is the picture. When the electric field is 0, you have same number of states on the positive side, same on the negative side, right? No reason to go one way or other. Remember the Fermi level, both sides equally feel, we are done. Current is 0 because plus and minus cancels. If you apply an electric field, but a low one, then of course you can see that some of the electrons will move on one side depending on the electric field, and the ones that are going opposing to the electric field, that number might change. The blue and the red one, the number is no longer the same. So therefore, the current has increased, right? Now you have current. If you apply a little bit more, then of course you have more red and less blue. So current is even more. That's very good. But the thing is, and you can see how I'm going along with the arrows on that silicon curve. But if you try to put any more, then it's not taking it anymore, because what happens that when it has that much energy, it is constantly scattered back, because anytime it's going at a very high energy, it's like a high energy collision. You know, it's when it scatters, many times the car completely flips around and goes in the opposite direction. So what happens beyond a certain point, after scattering, the reverse going one catches up with the one that is going in the forward direction. So beyond that point, the net flux doesn't change. Things get frozen in the proportion of red and the blue one. It cannot do anymore. You can see the black arrow I have shown for the red electrons. That is to indicate that at high field, constant scattering back essentially creates two streams which are one optical phonon away. And these two streams, the proportion of it cannot change. And as a result, current cannot change, and the whole thing saturates. Now, there's another very interesting feature of mobility or velocity for gallium arsenide, and that again happens at high field, not low fields. Low field, you see, everybody is the same, moving proportional to the electric field. Is only in the high field regime. And what is the high field regime here? About 10 kilovolts per centimeter, right? Beyond that, you are sort of talking about high field regime, this interesting phenomena occurring. Now, I'm talking about this gallium arsenide. There is a bump. So at certain electric field, lot of velocity, you put more, not only it saturates, but it actually goes down. Why is that? I mean, why putting too much is bad? The reason it happens is shown on the right-hand side, which is the EK diagram for gallium arsenide. Do you recognize it? This is a direct band gap material. You can see both at the K points are coincident on K equals 0. The gap is coincident on K equals 0. In the beginning, all the electrons sit in the little gamma valley, so a spherical gamma valley in gallium arsenide. You start putting an electric field. Just like in the previous picture, the red electrons and the blue electrons starts moving up in the EK diagram, right? With force, the K changes or momentum changes, it starts going up. Now, when it reaches a level, which is shown here in the red arrow, where it can not only scatter among itself, but its energy is high enough that it can go to the neighboring valleys. So there are valleys in the X direction, for example, also valleys in the L direction. What it will do, that now it has many places to go, right, after scattering, because they are all in the same energy. So after a phonon scattering, phonon has a lot of momentum. Do you remember? Indirect band gap recombination, I said that the phonon has a lot of momentum. It can allow you to go from gamma point to the X point or gamma point to the L point very easily. So here the phonon essentially can allow you to go all the way to the edges of the Brillouin zone. Now look at the effective mass. The effective mass, once the electron has gone there, it was happy to go there because it looked like a good place to go, lots of density of state. But as soon as it goes there, what's its mass? Its mass is very heavy, right? So it came in very happy, but as soon as it lands there, it realizes that my old effective mass, which is the curvature, right, second derivative, is much lower here. So now as if the mass of the car or mass of the electron effectively has increased. And as a result, what will happen, since velocity is inversely proportional to the mass, as a result, the velocity will go down. And that's why this is called a velocity overshoot. It's a very important phenomena. In many oscillators, people actually use this effect in order to, microwave oscillators use this effect because there's a negative differential region where you increase the electric field, velocity goes down, and you can make oscillators out of it. And that's a very important phenomena that one has to understand. Okay, and this is the last slide in which we just very quickly talk about how to measure it. In the last, all this is I talked about is theory. How do you measure mobility? Well, you put 4 contacts, 2 red ones that you can see. It's a top view of a sample of a silicon, 110, let's say, the green one. And you have 2 contacts, electron, you pump in electron through one contact and taking it out through the other one. And the yellow points are the voltmeter, where you measure the voltage between them. And you can see the electric field, when it's purely drift current, is proportional to J and proportional to resistivity rho. And the resistivity, because if you have both electron and holes, is given by that formula. And so the resistivity, if you equate it, you will get a relationship. But let's say it's primarily N-doped or primarily P-doped material, the green one, then one will be N or P will be much larger than the other. So for N-type material, Nd is much larger, let's say. So if I measured the resistivity as a function of Nd, then I can calculate the mobility, right? So that is the plot on the right-hand side. That's what you see, that doping on one side. So they prepare a set of samples, green samples of various doping levels, and they make the measurement of rho by measuring the current and the electric field. Electric field they obtain from the voltmeter by taking the voltage and divide by the length of the yellow probes, the difference between the yellow probes. And from here, they get it. Now, do you see that this is reflected in the experiment? Take log on both sides. This is a log rho, y-axis, log Nd on the x-axis. What should be the slope? -1, right? It should be -1. And you can see, indeed, the slope is -1. So experimentally, the theory we just developed is sort of reasonable. But in the next class, we'll say that putting it like Nd, what I said, and this saying it on the x-axis, this is Nd, it's not so easy. How do you know Nd, actually? You have an implanter. You implant some dopants in. How do you know some of them didn't go here and there, all went to the place you wanted to? How do you count ND? Now, that's not an easy thing. It's not like counting atoms in a silicon. So what I said, this axis, this x-axis, is not so easy to make. And that will be our discussion in the next class, that how do we understand the x-axis. So that's it. This is the summary. We started by thinking about various types of equations that we'll need in future classes, Poisson, and the drift diffusion equation. We talked about drift today, and the essential element is drift is mobility. We talked about mobility, but we thought at the end that we know how to calculate mobility. But the trouble is we don't know n sub d or n sub a. And unless we know that, we really don't know mobility. So that will be the discussion in the next class. Okay? Thank you.